Our next speaker is Dr. Nathan Gaw. He is an assistant professor of data science in the Department of Operational Sciences at the Air Force Institute of Technology at Wright-Patterson Air Force Base. His research develops new statistical machine learning algorithms to optimally fuse high-dimensional, heterogeneous, multimodality data sources to support decision-making in military, healthcare, and remote sensing. He received his BSc and MS in biomedical engineering and a PhD in industrial engineering from Arizona State University. Dr. Gaw was a postdoctoral research fellow at the ASU Mayo Clinic Center for Innovative Imaging and in the School of Industrial and Systems Engineering at Georgia Institute of Technology. He is also the chair of the Informs Data Mining Society and a member of IISE and IEEE. Thanks, Dr. Gaw.
Thank you. Hello, everybody. Hope you're having a great morning. Today, I'll be presenting to you, slightly more machine learning and AI focused talk with some calibration and statistics inserted into it. So we're looking into assessing the calibration and performance of attention-based spatiotemporal neural networks for lightning prediction. So here's a brief overview of the discussion where we'll first do some literature review, talk about our particular contribution, go over some of the methodology for particular neural network architectures that we'll be working with, building our experimental procedure, and then presenting some results on both the toy problem application with the moving MNIST dataset, as well as a real-world application called the storm event imagery dataset, coined the severe dataset. It was created by MIT AI Accelerator, and a great data set to have using remote sensing images to predict lightning strikes. And then we'll talk about some of the results, some of the pros and cons of some of these different proposed models, and then get into the discussion. So lightning is a naturally occurring phenomenon associated with thunderstorms, and it poses a very significant threat to life. In the United States, you could see lightning strikes have caused quite a bit of damage. We see significant damage to building fires in the realm of almost $500 million in damage, as well as causing many wildfires, 9,000 wildfires within a 4-year period, as well as various fatalities from direct strikes. Furthermore, weather delays, which include thunderstorms, cause significant number of delays to air traffic, which the Federal Aviation Administration estimates to cost billions of dollars when considering the impact to delays in flights alone. And the location and timing of lightning strikes is extremely difficult to accurately forecast. As we all know, we watch the weather news, every single night, and they predict it's going to rain, and it's a sunny day the next day, and we still have a lot to grow and develop in our ability to predict. So in the past few decades, researchers have turned to deep learning models to try to tackle this prediction problem. There are numerous branches within this tree. The first three that you see, convolutional neural networks, recurrent neural networks, and attention-based neural networks, they all have some similarity. We also add a little bit of spice with model calibration, to look at, how can we insert some statistics into these AI and machine learning models to assess their calibration. And so I really feel that, people in our field can provide a lot of benefit to folks in computer science who, primarily look at performance of models, but don't really think too much about their calibration. And so within these different neural networks, there have been numerous works done on weather prediction, both with non-attention-based models and attention-based models. We'll get into the meaning of those in just a bit, looking into applications such as radar, lightning, and tornadoes as well. And so our research will fall under these particular categories, looking at lightning and both the non-attention and attention-based models, and also examining model calibration for both of those. More specifically, we developed 3 novel sequence-to-sequence spatiotemporal neural networks that ingest a time series of multiple remotely sensed weather modalities to predict the timing and location of lightning strikes across a given area. Furthermore, to produce more reliable models, this research integrates the uncertainty associated with model predictions throughout the model development process by including model error into the tuning and training process. And we will also work with quantifying that error using calibration curves and a metric derived from those calibration curves called the expected calibration error. And so this research quantifies models calibration using both a qualitative method by looking at sample calibration curves, where you could see with this methodology, let me grab laser, there we go. Here, if you have a calibration curve where you plot mean predictive probability versus frequency of occurrence, if you have a perfect line here, you have a perfectly calibrated model. If you have under a confident model, you'll find a curve that lies slightly above this calibration. And if you have an overconfident model, you'll find a curve that lies slightly below. Now to provide a little bit more objectivity to this, we also calculate the model's expected calibration error. And this is a measure of how well a model's estimated probability of occurrence matches the occurrence of the events, which provides a summary statistic of the model's calibration. So moving on to the methodology, we'll look at the novel models, which we will develop, including the attention convolutional LSTM, the convolutional LSTM convolutional UNet, and the attention convolutional UNet. And so we'll get a little bit into the nitty-gritty about each of these different networks, and hope you're able to keep up with me. If you have any questions, though, more than happy to answer. We're first going to talk about a couple different attention mechanisms that are applied. Basic idea of attention mechanisms is we want to, not just train a neural network model to ingest images and produce an output, but we want to be a bit more intelligent about this and also train the model and tell the model where to apply attention to different parts of the moving image that's being inserted. And so our first attention mechanism is called the single self-attention mechanism, or SSAM, as we'll coin it for the rest of the talk. So this SSAM takes into as input this X image, which or video, which is a sequence of images, and applies three different types of convolutions, and these Q, K, and V vectors refer to query, key, and value, and they're all generated using three-dimensional convolutions on the input. And so once these Q, K, and V vectors are generated, a series of multiplication, softmax, and addition operations are used to produce the attended output X sub prime. The second self-attention mechanism is the dual self-attention mechanism, or the DSAM. This mechanism is specifically designed to follow a convolutional LSTM layer as it ingests a convolutional LSTM's output. Basic idea of a convolutional LSTM is it looks both at spatio and temporal aspects of your data. So if you've heard of convolutional neural networks, that looks primarily at images. If you look at LSTMs, that stands for long short-term memory. It's the most popular type of recurrent neural network, and so looks at temporal aspects. And so convolutional LSTM is a neural network that is designed to combine both of those aspects, both the imaging and the temporal. And so, as you can see, this takes as input, and does pretty similar operation as the SSAM does to obtain this HI sub t, which is basically, same version as a single self-attention mechanism. But additionally, we also combine this with another SSAM applied to this O of t, and this O of t prime is produced. And basically, H sub t is a convolutional LSTM's short-term memory and does not have an n deep sequence like O sub t. And so we're combining H sub t, short-term memory, with O sub t, a slightly longer-term memory, to get a little bit more of an evolved attention mechanism, considering both short and long-term memory aspects. And so with these different attention mechanisms, this SSAM and this DSAM, to keep the big picture in mind, we're looking at combining both short-term memory with the SSAM and longer-term memory with the DSAM. And so now that we see the attention mechanism building blocks that we've applied, we're now going to present several building blocks for each of these novel architectures that we're going to apply. This first one is the attention convolutional LSTM, which incorporates both the SSAM and DSAM into a general convolutional LSTM model design. And so you could see alternating layers of this SSAM and convolutional LSTM and DSAM, and this ultimately produces our predicted output, which will ultimately be predicting future occurrence of lightning strikes. This next second model is the CCU, which uses a stacked convolutional LSTM and 3D convolutional layers and a UNet style in an encoder decoder model. And this third model is the attention CCU. So it's designed to mirror that of the CCU, but incorporates SSAM into every computational layer, into the encoder decoder. Again, trying to train the model to identify which areas in the image and the video to pay the most attention to. And so of note, these models are designed to ingest a time series of images, X of t, and produce, so it can be any type of video. So any type of data set that has both spatial and temporal aspects associated with it. And so the output here will be to predict future occurrence of whatever you are interested in, pixel by pixel in the output image. And so you'll see a few examples to see what I mean. So to determine if the models are any good, they are compared against model architectures seen in previous weather research. So this includes convolutional LSTM and UNet architecture inspired by previous lightning prediction research, and also a modified UNet to include 3D convolutional layers since we're looking at three-dimensional data. And then CNN architecture motivated from 3D CNN tornadic prediction, in which the third dimension is time. And so these 3D CNNs are not necessarily built to incorporate the temporal aspect, but you can, in essence, incorporate the temporal aspect by the third dimension of time. And then to compare our attention-based models against other attention-based models, an attention UNet that we've seen in medical research is used, and the SSAM is added to a general 3D CNN framework to produce an attention 3D CNN. And so now that the model architectures are established, it's determined that the best loss function to train the models is with this weighted binary cross entropy method, where we chose this because the data is quite imbalanced. And so when you think about some streaming video of lightning that's coming in, you have very large swath of land, and both in space and time, it's extremely sparse in terms of when the lightning will strike. And so our data set can be very imbalanced, where we have quite a few number of instances where lightning does not occur, and only a handful of instances where it does occur. And so we want to weight more greatly those particular instances where lightning occurs. Those are the more crucial aspects. And so weighted binary cross entropy addresses this issue by applying positive and negative class weights, where our positive class weight corresponds to the minority class, and our negative class weight corresponds to the majority class. And it penalizes a model more for making incorrect predictions when a positive event occurs, which for our application, we don't want to make a mistake, especially when lightning occurs. It's better to be a little bit more cautious in regards to that. And so this will encourage the model to predict minority class more frequently. And then label smoothing is also incorporated to attempt to improve model calibration and accuracy. So moving on to the experimental procedure that's implemented on both data sets in the study. This data is first pre-processed, which entails any data scaling and binarization. We also do splitting. So we split our data set into corresponding training, validation, and test sets, and generate the input and target sequences in each set. We'll talk about the data sets in just a moment. And then we also tune our model architectures by finding optimal hyperparameters and utilize Bayesian optimization with Keras Tuner to identify optimal values for these particular hyperparameters. And every model is tuned to maximize something called the critical success index, which is a very popular index used in weather prediction. Basic idea of it is the number of correctly predicted events over the total number of warned events and also true events that were unwarned. And so afterward, we evaluate the tuner models looking at the loss function, this critical success index, which we just introduced, and this expected calibration error for predictions of every tuner trial. And three-dimensional Pareto front is used to identify which trial models produce minimum loss, ECE, and maximal CSI values. And these become the Pareto solutions. We have a longer version of the presentation where we get a little bit into the nitty-gritty in regards to that. We've abbreviated that part just to present you the final results. And so, we also look into scoring the tuner models and scale the loss, ECE, and CSI values of the Pareto solutions. And the scaled values are evaluated with the scoring function, and hyperparameters from the trial model with the lowest scores maintained for training. And for this particular model, we equally weight the loss, the CSI, which we want to have, so the greater the CSI, the better. So we do 1 minus there. So it's commensurate with the loss in the ECE. And then we also train 15 models for each of the archetype, where each model is randomly initialized. This is really to insert some statistics into this AI and machine learning. And we evaluate the trained models based off of CSI, bias, precision, and recall. And so you can see how each of these are calculated based off of true positives, and false negatives, so you can get a general idea for how each one of these work. And then we compare the model performances. We look at both the calibration curves, and we use the Mann-Whitney U-test for pairwise model comparisons between those different models. And so this is our toy problem application. So this is called the moving MNIST dataset, and it's used to ensure that our model architectures work properly, a very controlled environment. Basic idea of moving MNIST, it's the same MNIST dataset using handwritten digits, but now it gets a little bit crazy because you have two different digits moving around in a box. And basic idea of this is we want to try to predict the future movement of these digits based off of our previous knowledge, based off of the previous sequence. And so for this one, we have a sequence of 20 images for which we insert the first 10 images to be used in prediction, and then use the model to predict what is the next 10 images going to be pixel by pixel based off of the movement that has been seen previously. And then for our real-world application of lightning prediction, we use the severe weather dataset from MIT Lincoln Labs. It contains over 10,000 thunderstorm events, a very clean data set, spanning 3 years across the continental United States, where every storm event contains 4 hours of 5 types of remotely sensed imagery measured in 5-minute increments, supplying 49 images of each modality for every event. And so here we have 5 remotely sensed modalities where there are 3 satellite modalities. We also have vertically integrated liquid, which actually is one of the more predictive modalities for lightning because, it looks at really, liquid is highly associated with conductance of electricity. And so when you have clouds that are stacked up very high and this liquid is very concentrated, it provides a conduit for the lightning to strike more quickly. And so when you see some of those patterns, that provides a nice prediction for you. And so for this research, we use 30 minutes of the satellite and also the vertically integrated liquid, for the reasons that I just said, to predict the location of lightning strikes over the next 30 minutes. And so, thinking about things like launch schedules for rockets and other aspects, thinking about safety, if we're able to predict what is going to happen 30 minutes in advance, this can actually be quite useful technology to use for the future if we get really accurate in regards to that prediction. So looking at the calibration curves for our trained models, we see that all of the models that we have are overconfident in predicting the positive class in both experiments. This is a very interesting thing to note. And again, I encourage you guys, I'm trying to interact more with computer science folks more and more these days, attending conferences. There are, some issues, some statistical issues with convolutional neural networks and some of the neural network models that they're training, where there is not as much robustness. These models can be overconfident in regards to their prediction. And so looking at these models, with that said, we do see in general that the attention CCU, the CCU, and the UNet architectures displayed the best calibration, particularly in the lower probability bins among the 8 architectures in both experiments. And so these are ones in particular to look at, to think about, what properties of these make them less overconfident than the other models. And so this is the first chapter of my PhD student's dissertation. We'll be looking at, in the third chapter, doing a design of experiment study to examine different components of these networks to determine, what aspects of a neural network make it better calibrated than others. And so that will be some continuing research. But this is something, and an interesting alarm, to share with CS folks and machine learning folks that you might know, that we shouldn't just focus on model performance and not even just necessarily uncertainty quantification, because that's also an aspect that people are looking at, but even thinking about calibration of the model and assessing confidence and accuracy and how they're related to each other, I think is extremely important. And this just belays the fact that these models in general are overconfident in their prediction. And so moving on to the performance metrics from each model design in both experiments, this table displays the average metrics from the test set evaluation for the 15 models ran for each of these. A lot of computation done by my student. So the up arrow, down arrow, or 1, represents the desired value of the metric. So in the CSI, the higher it is, the better. For this ECE, the lower it is, the better. And then for this bias, the closer it is to 1, the better. And so you can take a look at this table. And I also put down this star and this plus and this diamond to denote the first, second, and third best models. And the bold values on the table indicate that the value is significantly better at the 95% confidence value in all 7 of the pairwise model comparisons with the Mann-Whitney U-test. And so also metrics that have duplicate symbols indicate that there's a tie for that particular position. And so to summarize this table with lots of numbers, basic idea is the attention CCU, so the ACCU, the UNet, and the CCU architectures are the top performing architectures across both experiments, where we see MNEST here and severe here. And the ACCU attains the highest average CSI value on the real-world test set and is in the top 3 performing models for precision, bias, and ECE metrics. And it's especially important for CSI, specifically in this area, because this is a metric of primary interest when you look at these lightning prediction papers. The UNet is in the top 3 models for all the metrics in the toy experiment and is in the top 3 models in the 4 of the 5 metrics on the real-world data. And the CCU is in the top 3 models on 2 toy set metrics like the UNet, and is a top-performing model on 4 of the 5 metrics in the real-world experiment. And so one thing to note also is that the attention CCU was not a top-performing model. regarding recall in either of the experiments, while the UNet and CCU were in the toy experiment. However, both of these architectures attained higher bias values than the ACCU, indicating that they tend to predict the positive class more, leading to higher recall values. And so, yeah, for those of you statistics nerds, that's just a little bit of additional trivia to think about in regards to these models. Now to show you a little bit more, a little bit more high level about what these models can do, I'm going to present to you some sample output associated with these models. So we identified that ACCU seems to overall perform the best in regards to most of the metrics. And so here at the top, we have the model predictions for this ACCU, where you see a general color map as well as some demarcations for where is, how confident is this model, or what is a specific value that this model is predicting, saying the probability that there is going to be lightning in this particular area. And so you can see here across this time sequence that it seems to be relatively accurate when you compare it to the observed lightning strikes. We specifically calculated the metric by choosing the threshold that's above this 0.45 prediction value. And you could see overall that it captures, at least general trend of where lightning exists. Now for, some other case where, lightning might be a little bit sparser and we want to be a bit more accurate and precise with identifying where the lightning is. We have another example of this output where you can see, general binary predictions do produce this cloud, in the upper part of the image, which matches pretty well with the observed lightning strikes. And so, one thing that I will say about this is, it does seem to be, again, you can actually kind of see an example of overconfidence in regards to prediction, and even a little bit more of a bias to predict the positive class. But operationally, you could see that it captures just this general cloud of interest, associated with where this lightning strike is. And so in summary, the ACCU architecture attained the highest accuracies in both experiments, displayed decent calibration, though it was still a little bit overconfident, and was the top performing model in most of the remaining metrics. Furthermore, the performance of the ACCU in terms of its lightning prediction capabilities are comparable to the performance of models seen in previous literature. The CCU model architecture also performed very well in both experiments, and it was generally seen in the top performing model. And so we seem to, this seems to indicate that this general UNet architecture seems to perform better than, the general convolutional LSTM architecture. And so in terms of overall performance, the attention convolutional LSTM exhibited the most modest performance of all of our novel proposed architectures. And because it was never a top performing model. And the attention CLSTM achieved far superior performance than its non-attention based counterpart, suggesting that the inclusion of attention mechanisms into the model provides dramatic increases in model performance and stability. And so not just inserting an image to the model, but also training a model about where to look for lightning prediction. And so, with that said, it's also been observed that including attention mechanisms didn't always improve the model performance, which counters the prevailing thought that attention generally improves model performance. And so, for instance, the UNet outperformed the attention UNet in all the metrics except the recall. And so, furthermore, in the real-world experiment, there's not evidence to conclude at the 95% confidence level that there is a significant difference between the performance of the attention CNN and CNN in 10 metrics. And so we do see that attention doesn't necessarily improve across all different model architecture types. And we still don't know exactly the reason why. Again, it's work for my PhD student in his third chapter of his dissertation to determine why exactly is this not always useful in these different model architectures. So hopefully you find something interesting. And then all of these, so we also saw in totality all of our trained models in both data sets were overconfident and generally attained higher than desirable biases. And the overconfidence and high bias are linked to models overpredicting the positive or minority class. And so you saw a little bit of an example of that, especially in that second prediction that I showed you. There's a little bit of an overprediction, a little bit of a cloud that was produced where we had more lightning strikes predicted than there actually were. And so more specifically, with the weighted binary cross entropy, a low loss function value can still occur when the model overpredicts or is biased toward positive class, especially if the ratio between the positive and negative class weights is large. And so during our tuning process, models which achieve minimal loss and that are Pareto solutions may do so by being biased. And so these low loss values are then equally weighted in the scoring function, which may lead to choosing optimal hyperparameters that inherently favor a bias model. So this suggests that in future works that utilize this approach with an imbalanced data set, we should consider some type of different weighting score function. And so that will be one of the concepts that we're going to examine in future experiment. And so finally, we saw that that these imbalanced data sets, for these imbalanced data sets, the expected calibration error didn't describe how well calibrated a model was, indicating different calibration methods may be preferable when dealing with such data sets. And so we'll also be looking at formulation of this expected calibration error. I think, especially in this slightly newer field, that's very applications focused. There's a lot of metrics that these subject matter experts have used that may not be the best metrics to use for training their models. And so one key thing, especially when we're introducing AI, machine learning, and also ensuring proper calibration of these machine learning models, we want to make sure that there's decent robustness in regards to that. And so so moving forward, we will be investigating the effect of attention mechanisms on model calibration, looking at whether attention mechanisms inherently improve model calibration, where in the model design do attention mechanisms provide the most benefit to the model. We'll also look into building a better Pareto scoring function and looking at combination of metrics that will produce inherently unbiased models. And finally, apply methodology to other dangerous weather phenomenon. And so one fun thing for chapter 2 of my PhD students' dissertation is we're going to be looking at tornadoes. Just a couple weeks ago, we had a tornado tornado warning in Dayton, Ohio. We all hid in our basements and hid in our apartments. Air Force, let us out 2 hours late. And lo and behold, there was no tornado. And so we're interested also in, seeing, is there a better way that we can predict tornadoes and accurately determine, will there be one or not? And so, definitely it's good to exercise caution in regards to that. But that's also, one motivating thing and some way that we plan to expand our research. And so with that, I'm open to any questions that you guys have for me. Not sure where the time is at in regards to that. I tend to talk a little bit. Okay, we'll have room for a question.
So you pointed out how the probabilities you get are overconfident and not necessarily well calibrated. So there's a funny trick I've seen in machine learning, which sounds kind of hackish, but basically you fit a logistic regression on top of the predicted probabilities, as referred to as Platt scaling. I'm curious if you've tried that and if that helps calibration.
So we might have done something, but probably not as comprehensive as Platt scaling. That's actually an interesting idea. I'll share with my PhD student. The most that we've done is, applied some label smoothing, and, that might have some indirect effect, that might work toward the Platt scaling, but that could be nice, robust method to try and see.
Thanks.
You mentioned earlier when you were doing your model formulation that you had sort of a regularization term for having the attention network predict lightnings more often because you didn't want to risk not predicting lightning when lightning would occur. Do you know how much that contributes to your dip in the overfitting plot? Do you have an idea of?
So I'm not sure, but that we do suspect that could be one of the major contributions to that overconfident prediction. Yeah, it's a relatively common practice done in this general application area. Yeah, using this weighted binary cross entropy, and so yeah, kind of like what we talked about. Yeah, in the discussion, I think that there may be something with this weighted binary cross entropy that causes a little bit of overconfidence in prediction, especially with this imbalanced data set. So yeah, that's a very good observation.
Okay. And just a quick comment on the overfitting plot as well. I think a lot of people, for binary, it's probably justified to say, let's compare probabilities to fraction of positives. But when you move to n-class classification, the nets aren't really giving you a probability distribution. They're not really probabilities, right? That you can't, there's no countable additivity that it's accounting for in the code and guaranteeing you that. So I don't know how meaningful it is to compare fraction of positives to predicted probability when you have more than one classification.
Yeah, that's a great observation, and I think that these neural networks are very different paradigm, I would say, than traditional statistics, and there's a lot of I think there's a lot of loose ends to think about how to make these more robust, how to apply greater probability to these. We're looking into some Bayesian neural networks which can incorporate probability more into the estimate, have something that's more robust. But yeah, you are correct in regards to trying to match these up with some traditional distributions. That's not always realistic ask in regards to these models. So yeah, great observations. I appreciate that input.
Right, let's thank our speaker.